I thought I might quickly start to rough out some solutions for anybody who wanted a little bit more help with this homework problem. I know sometimes the cylindrical geometry can stump people a bit. So we have a insulating cylinder of charge, and the net charge is uniformly distributed throughout its volume. So let's say our charge is positive. It means that amount of charge is evenly spread out everywhere. There's no spot that has more charge than another. Okay, so imagine all those pluses are absolutely evenly spread out. We'll use Gauss's law to solve this problem. Gauss's law says the net electric flux is the integral of E dot dA, so the electric field over some closed Gaussian surface, is equal to the net charge enclosed by that Gaussian surface divided by epsilon naught. So when we did our sphere of charge, we used spherical symmetry to pick our Gaussian surface. This time we're going to use cylindrical symmetry. Our charge is a cylinder, so our Gaussian surface should be a cylinder. We're going to be finding the electric field inside the cylinder and outside the cylinder. So ultimately, we'll be drawing Gaussian surfaces, one of which is going to be inside. So this Gaussian surface is a cylinder inside our cylinder of charge. It has radius r and length L. And we'll also need a Gaussian surface that's outside our cylinder of charge. It also has radius r and length L. Okay, let's try and find the integral of E dot dA for both these surfaces because the result will be the same because the geometry is the same. In our Gauss's law, the net electric flux, which is E dot dA, is going to have a flux. Oops, I wrote a Q instead of a flux. There's going to be a flux through the top surface, so this one right here. There's going to be flux, or we'll have to consider the flux through the bottom surface. And then we also have our flux through the walls of the cylinder. And if this sounds familiar, it's because this is the same process we did when we did our long line of charge. So you may have to review that if you're feeling a little stuck here. For our electric fields, we know that the electric field due to a cylinder of charge, a long cylinder of charge, will point radially outwards, all along the entire line of charge. Okay, that's true for both of these. I'm just sketching it real quick here. Hopefully you get the idea. Trying to draw it in 3D, even though I am definitely not an artiste. So there's our electric field. The electric field is radially outwards. My electric flux through the top of the cylinder is the integral of E dot dA. For dA, we mean a little bit of the area on the top face of the cylinder. So let's identify a little bit. We'll just draw that in. We'll label it dA. We can do this on both at the same time to see that they're the same. Our dA points radially outwards from the surface, so it's straight up, and our electric field is perpendicular to the surface. Those two things are perpendicular, so the scalar product is equal to 0. Same thing is going to be true on the bottom. On the bottom surface, dA points straight down. The electric field is radially outwards, so the net electric flux through the bottom is also 0. Okay, so just like it was on the top, it's also equal to 0 on the bottom because they're perpendicular. Okay, that leaves us with the walls of the cylinder. This slide's a bit full, so we'll work on the next slide. For the walls of the cylinder, start with the same expression, the electric field dotted with dA. Let's draw our little bit of dA on our cylinder. So the little bit of dA on the wall of the cylinder is going to point radially outwards, whether we're going on the big cylinder or the small cylinder. So dA is radially out, electric field is radially out. Those two vectors are parallel. So you might notice time and again that the symmetry is such that the angle is either 0 or 90. And we pick our Gaussian surfaces so that that's what we have. So this time our angle is 0. That leaves us with the electric field of E times dA because cosine of 0 is 1. If we're a constant distance away from the center in this sort of symmetry, the electric field is going to be a constant, so E comes out front. The integral of dA is just A. A refers to the area of the wall of our Gaussian surface. So the area of that wall is going to be E times 2 pi r times the length. Okay, so now we have a way to find the net electric flux. So the net electric flux is the flux through the top plus the flux through the bottom plus the flux through the wall. So our net electric flux is equal to E times 2 pi r times L. We're going to put this together with the rest of Gauss's law to find an expression for the electric field. So we've got half of our Gauss's law done. We know the net electric flux is E times 2 pi r times L, where L is the length of our Gaussian surface. Next, we have to deal with the Q inside. That's going to be different whether we're inside or outside the cylinder. So let's start with R less than A. If R is less than, oh my goodness, not A, capital R, which was the radius of the cylinder. So our cylinder had radius capital R. So if R is inside the cylinder, then the net charge enclosed by our Gaussian surface, Q in, since this is a three-dimensional object, Q in is going to be the density times the volume of the Gaussian surface. So the volume of our Gaussian surface is the volume of that cylinder, which is pi r squared times the length of the cylinder. Okay, let's put it together. The net electric flux is E times 2 pi r times L. It's equal to Q inside, rho pi r squared L divided by epsilon naught. Okay, let's see what cancels. We've got pi on both sides, so we'll divide by pi. Let's divide both sides by r. That leaves us an r on the right-hand side. Let's divide both sides by L. And I think that's all that we can cancel. That leaves us with the magnitude of the electric field is the density, the charge density of the cylinder times r divided by 2 times epsilon naught. Because our electric field is a vector, we say that it points radially outwards. Okay, so that's inside the cylinder. What about outside the cylinder? So if R is greater than R, have to find our charge enclosed. So our charge enclosed when we're outside the cylinder is just however much charge is on this bit of the cylinder. Okay, so we find out how much of the cylinder is inside, we multiply that by the density. So times volume, density times volume. Density, the volume of the cylinder that's inside the Gaussian surface is pi times the radius of the cylinder squared times L. So we'll put this together. Our net flux, E times 2 pi r times L equals density times pi times the radius of the cylinder squared times L. Solve this for E. We notice we've got pi. Oh, I forgot to divide by epsilon naught. So easy to drop a symbol when you're working through these things. Divide both sides by pi, divide both sides by L. We don't get anything else that cancels. We're left with our electric field is equal to the density rho times r squared divided by 2 times epsilon naught times r. Again, it's a vector, so we would say the direction is radially outwards. So there's the electric field inside and out. Last step, we'll just make a plot of that. In a plot of this electric field, we'll put our electric field on the vertical axis. We'll put our distance from the center on the horizontal axis. When we're inside the cylinder, the electric field is proportional to the distance from the center. That means it's linear going up through the center. So this is linear. And the cutoff point there is when we're at the surface of the cylinder. Once we're outside the cylinder, it falls off as 1 over r. Our maximum value of electric field happens here where r is equal to r, and at this point the electric field is equal to the density times the radius, so we plug in that little r is equal to the radius, big R, divided by 2 epsilon naught, and we get that expression whether or not we put r equals r in this expression or this expression.